Good afternoon. We're Group 4 from Section 905, and today we're excited to walk you through our project proposal for a magnetic levitation system. Our team includes myself, Kamalika, along with Emma and Enrique. Our project combines mechanical modeling, electronics, and real-time control to create a visually striking and technically challenging system. We chose this topic not just because it's cool to make something float, although that's definitely a bonus, but because it touches on a lot of fundamental concepts we've learned in class and puts them into practice.
You can find the YouTube link videos here and the team folder link here.
Our magnetic levitation system is designed to suspend a small magnetic object, like a disk, in midair using only electromagnetic forces. There's no physical support keeping it in place, which makes it an unstable system by nature. To accomplish this, we'll apply varying levels of current to an electromagnet. This current creates a magnetic field, and as it increases or decreases, it affects the vertical force acting on the object. The trick is maintaining just the right amount of force at any moment. That's where we'll use a PID controller, a proportional integral derivative controller, to keep the system stable in real time. It will continuously adjust the current to correct for any disturbances or drifts.
Here's a tiny clip of what we're trying to accomplish. As you can see, as the object gets closer to the magnet, it starts floating, but it still shakes and wobbles a bit. This idea is rooted in the physics of electromagnetism and dynamics. When a current flows through a coil, it generates a magnetic field. If you place a magnet or a metal object near the coil, the field can attract or repel it. What we're doing is balancing two forces, gravity pulling down the object and magnetic force pulling it up. We're trying to reach an equilibrium point, but this isn't a naturally stable system. If the object moves even slightly out of position, the forces become unbalanced. That's why real-time control is key. Our system needs to react quickly to any motion and correct it before it gets out of control.
To build this, we've broken it down into three main domains: mechanical, electrical/computer, and simulation. On the mechanical side, we've already started by deriving the equations of motion for how the disk moves vertically. We'll use a camera system to track the object's height and feed that data into our controller. For the electrical and computer side, we're using an Arduino microcontroller to adjust the voltage going to the electromagnet. We'll also solder a PCB with all necessary components. Lastly, we're using MATLAB Simulink to simulate how voltage changes affect the magnetic field and how that field moves the object. This gives us a virtual way to test the control system before we try it physically.
To stay organized, we divided the tasks based on each of our strengths and interests. Kamalika is in charge of 3D printing the design, implementing the PID control system on Arduino, and soldering the PCB board.
To create the electromagnet, a copper wire will be wrapped around several batteries to generate a magnetic field, which will be measured using a Hall sensor.
I'll be deriving the equations of motion that relate magnetic force to the position and handling physical measurements of the object's height and compare those results with the experimental data from Simulink. Will also help with assembly and integration of all parts. Enrique is handling the CAD modeling of the base and developing the Simulink models that convert voltage inputs into magnetic force.
In SOLIDWORKS, I will build a case that holds the electromagnet on the top and both the Hall sensor and the distance sensor directly at the bottom of the electromagnet.
We're working collaboratively across the board, but this structure helps us stay efficient.
We map out our project over 4 weeks with clear milestones. In week 1 and 2, we'll focus on designing and manufacturing. I will CAD the parts, Kamalika will 3D print them, and Emma and I will work on soldering and initial assembly. In week 3, we shift to simulation. Emma and I will work together to derive the governing equation and build Simulink models. Week 4 is for physical experimentation. We'll gather data from the levitation device, fine-tune the controller, and make final adjustments before our presentation. Having a clear schedule keeps us on track, and we'll build in time for testing and iteration.
So what do we hope to accomplish? First, we want to be able to control the object's vertical position by changing the current through the electromagnet. Second, we'll measure the magnetic force and resulting displacement of the object so we can tune our system with real data. Lastly, we'll compare our simulations to the actual behavior of the system. This helps validate whether our models and assumptions were accurate.
To wrap up, this project is more than just making something float. It brings together mechanical design, dynamic system modeling, electronics, and real-time control. It's a great way for us to apply what we learn in a tangible and exciting way. We're looking forward to building it, troubleshooting it, and hopefully seeing that this hovering steadily when it's all done.
Thank you all for listening.